Hello everyone, and welcome to the first module of Introduction to Continuum Mechanics. In the first part of the first module, we're going to elaborate on summation convention, or so-called Einstein's summation convention. Then we discussed the Kronecker Delta and the permutation symbol. So let's get started with Einstein summation convention. Suppose that you have an expression like alpha equal to a1 x1 plus a2 x2 plus some other terms plus a n x n. So here you have a series of terms which are summed, and you have different subscripts here, like 1 here, 2 here, where these actually are repeated, and then you have a summation on the whole, let's say on the whole uh, expression. So we can rewrite this as let's say sigma with capital, of course. So a I x I varies from 1 to n, and n here can goes to whatever you want, whether it could be infinity or a finite kind of value. But you can also write this as, for example, summation of aj xj, where j starts from 1 and goes to n, or whatever kind of subscript you can select. For example, you can rewrite this as a k x k. K varies from 1 to n, of course. And you will see that in all of these here, there is no major difference between all these expressions here, despite the fact that their subscripts are different. Their subscripts are different. We call these kind of subscripts like, let's say, I here, J here, and K here as dummy. Let's say, let's write it here. So maybe I change this to the red one. So we call these as dummy indices, or right here, a dummy index. So we call I, J, and K dummy index because they're simply a placeholder. So they're just used to rewrite this summation here in the form of let's say a shorter format here. So we call them a dummy index. So we can simply rewrite this as, let's say, alpha equal to ai xi. So here we let's rewrite this as sigma ai xi. I varies from 1 to n, and simply here we actually drop this this sigma sign here, so we can simply write it as AIXI. We can also do the same for these two terms here. So we can rewrite this as AJXJ equal to AKXK, or whatever, for example, ASXS. And this kind of, shorthand of writing has been first developed. It is first attributed to Einstein, and Einstein developed this during his work on the quantum mechanics, because there were so many long expressions that he had to term them into shorter ones. So let's write one of these expressions here. For example, first let's say that n goes to 3. So alpha becomes, if we write AI xi, and so n varies from 1 to 3, so we'll have a1 x1 plus a2 x2 plus a3 x3. Or for example, if n goes to 2, we can rewrite this as aj, for example, xj, a1 x1 plus a2 x2 here. And as you see here, we see that the number of the terms here actually varies with the, let's say, the with this pattern that you have this n here, so it is 3 to power of the number of dummy index that you have. So for example, here we have this I here twice, so this is a dummy index because this is repeated twice, so we call it a dummy index. We will elaborate on this later, but here you have I here, and this is a dummy index, so I will say that we have 3 to power 1 terms, which is obviously 3. Or here, you can see that we have 2, here n is 2, here we have j and j, so we have, let's say, to power 1, because we have j as the dummy index, so this becomes 2. And these are the number of terms. So in order to get the number of terms, we can write simply the last let's say term in series to the power of the dummy index. And in continuum mechanics, we work with n equal to 3 because we have like x, y, and z. Or for example, we work in plane, so we have x and y, so we do not exceed more than 3. So in continuum mechanics, let's abbreviate it as CM. Let's make this clear here, that whenever I use CM, I mean continuum mechanics. So in continuum mechanics, we do not exceed n equal to 3. Therefore, we have this n, let's say 3 here, to the power of dummy index. So this is called the Einstein summation convention. But we also have some other things that we have to take care of. So now we know what is a dummy index. So a dummy index is just a placeholder. Or let's rewrite this. So a dummy index is an index in, of course, in the summation convention, which is repeated twice. And this is quite important because in the second part, we also agree that an index should not appear more than twice on each side of the equation. And we also agree that, or let me write this maybe later. Yeah, because now I'm gonna, yeah, let's just write this later. Okay, so here, what does this expression mean? So it means that if you have something like alpha equal to ai x I, let's say yi, you don't have something like this. This is completely incorrect. You can't assume something like this. So at maximum, you have two repeated index. So if you want to write something like this expression, then you have to write it like this. So you have ai, xi, yi, and you write as sigma, capital sigma, here, where you can say, okay, I starts from 1, and for example, it goes to 3 or to n, for example. This is the correct way. So if you want to write something like this, so you have to put this capital Greek sigma here beforehand. All right, so let's get to some other, let's say, expressions. Like, for example, if I have AII or AII, what does it mean? So it means, in continuum mechanics, we are talking, of course. So it means A11 plus A22 plus A33. Or, for example, if you have, let's say, an expression like alpha equal to, let's say AI J X I Y, let's say X J. So what does it mean? So it simply means that you have two repeated index, or you have two, let's say, dummy indices. So you have to sum over the repeated indices. So maybe it's a good idea to write it here. So we sum over the repeated index or indices, of course. So here we also sum over the repeated index. So let's get started with I equal to 1. So we can say, okay, I is 1. So I just first put I, or let's write it here. So I will write it here, and then I will remove it. So I is equal to 1. So I have A1J X1 XJ plus. Then I then I equal I equal to 2. Then I will have A2J X2 XJ plus, and I gets 3, so it becomes X3J X3 XJ, of course. So now it's time to switch to J. So if J is equal to 1, then I will have, or let's write it here, then I will have A1 X1 X, let's say 1 plus A21 X2, or J is 1, X1 plus X3 1 X, oh sorry, this is A here, and this is of course A. So X3 X1 plus, so now I say, okay, J is 2, so I will have A so I put j equal to 2 here. So I have a2 x1 x2 plus a2 2 x2 x2 plus a3 2 x3 x 2 here, and then I switch j to 3, then it becomes a equal to 1 3 x1 x3 plus a2 3 x2 x3 a3 3 x3 and remember here that during writing the expressions here, I actually had an I over here when I wanted to substitute j with different values from 1 to, let's say, 3. So I will have an expression like this, and as you may come to this conclusion here, so we have this equation here. So the last term in the series, which is 3 for us here in continuum mechanics at most. So we have 3 to the power of dummy indexes, and this is the number. So the number of the terms is 3. So we have obviously 2 let's say dummy indices, I and j. So they repeated twice, so I is 1 and j is also 1. So we have 2. So 3 to 2 is 9. And when we count these terms here, 1 2 3 4 5 6 7 8 9. So we have 9 terms here. And this is way too beautiful to write long expressions. So now let's get to the free index. What is a free index? A free index is an index which is only repeated once on each side of the equation. So at the third agreement, if a subscript appears once on one side, it must, or let's say should here, better, so I prefer this, should appear once on the other side. And this is, of course, a free index. So, for example, if I have alpha equal to AI xi bj, here j is a free index, and since and this is the and let's say that these are the dummy indices, the dummy index. So here you have I as the free as the dummy index, and you have j as a free index. So it appeared here once on the right hand side of the equation. So it should appear once on the left hand side. So this justifies here where we had alpha equal to aij xi xj, and since we had two dummy indices I and j, so we didn't have anything here on the left hand side. So now let's see how we can write this expression here, this one. Okay, so if I say that so alpha j is equal to ai xi bj, so this is equal to, if if it gets I equal to 1, so A1 X1 BJ plus, because we said that we sum over the repeated index. So A1 X1 BJ, A2 X2 BJ plus A3 X3 BJ. And I changed I from 1 to 2 and then from 2 to 3. But what about this j here? It is a free index. How we can write this? So then you have to break the expression into different expressions here. So you have your alpha j, or better say that, okay, this alpha is equal to alpha 1, alpha 2, and alpha 3, because we are changing j from 1 to 3. So for j equal to 1, we have alpha 1. Then we have a1 x1 b1 plus a2 x2 b1 plus a3 x3 b1. And for j equal to 2, then we have a1 x1 b2 plus a2 x2 b2 plus a3 x3 b3. And then we have for j equal to 3, a1 x1 b3 plus a2 x2 b3 plus a3 x3 b3, of course. So you will have 3 different expressions. So the number of expression is equal to n, or here we said that in continuum mechanics we had at most 3, to the power of the free index. And here, therefore, the number of terms is 3 to, okay, how many free index do we have here? So it is only 1. It is j. 3 to power to 1, so it is 3. So we have 3. Let's expand this. So let's say that we have an expression like, let's say Tij is equal to A IM AJM, as is given in the book. So here, let us distinguish the free index, the dummy index first. So the dummy index, we said, is the index that is repeated. And it is repeated, of course, here, M. And we also have the free index, I and J, because they are repeated only once here. So I and J, I and J are the free index or indices here. So the number of different expressions, the number of, let's say, expressions is, and here you have the number of expressions, you have the number of terms, you have the number of, let's write the free index first. So you have 3 to 2, you have 9 different expressions here. So you have, for example, you have your expressions, ranges from T1, 1, T1, 2 to T3, 3. So you have 9 expressions here. 9 separate expressions here. And you will have here the number of terms. So you have only m as the dummy index. Therefore, you have 3 to 1, which is 3. So you will have something like this. So it is 1, 1, j is also 1. So it is 1, 1 plus 1, 2, 1, 2 plus 1, 3, 1, 3. And this actually goes down until the end. So for example, for the last one, you will have I at 3 and j at 3. So you will have so 3, 1, 3, 1. J is also 3, 3, 1. So you have plus 3, 2, 3, 2 plus 3, 3, 3, 3. So now you know about the free index and the dummy index here. So let's get to a kind of expression here, which I'm going to show you. So you know that a vector has a magnitude. So we have a vector. A vector has a direction. A vector has a direction, and it also has a magnitude. Right? So whenever I say, okay, A is a vector, so it has a direction and a magnitude. So I can say that, for example, this A here, I can decompose it into 2 parts. I have, let's say, my X and Y here. So I can decompose this into 2 parts. So the one that is in, let's say, A1, we call it X1, for example. Somehow it is not correct, but let's write it this way. And this let's write this as A1, X2. Sorry, is sorry, this is AX1 and AX2. But you know that we cannot write this as X1 and X2 because these are the unity values. So these are like the this gives the direction. So this carries the magnitude of the vector you have, and this gives the direction of the vector. So normally we rewrite this as E1, for example, and we put a caret sign here on the top, and this is AE2. So we can say that A can be decomposed into A1 and AE1 and AE2. And of course, you can just expand this into, just extrapolate this into the 3D. So you will have, for example, an expression like a vector like A as AE1 plus AE2 plus AE3. Okay, so so this gets back to X, This is in direction of y, and this is in direction of z, of course. So using the summation convention, you can rewrite this as a I, let's say a e I, for example. And you have to take care that a here is a vector. So we can rewrite this as a. So by dropping this this arrow sign here, you can rewrite this as let's say a. This is a bold a equal to, this is the magnitude, so I do not bold it here, and then I will have ei here. And you know that this is the magnitude, so it doesn't carry any subscript, but this is a subscript here, and it is repeated once, so it has to repeat it on the other side. So I write this as I again here, and in the next level, let's say that this is the bold a, I equal to a, which is not bold. So we have ei, so we'll also drop this here, this hat here, and this is e. This is also bold. So you should know that this is a vector and this is a vector, right? So these are different from this magnitude here. But during writing, I simply write this as, let's say, AI is equal to AEI. So when EI comes, so you know that this gives the direction for what we want. So if you have, for example, the magnitude, if you want to have the magnitude of, let's say, a vector like a, so you can simply write a, the magnitude is equal to AIEI. And of course here you have this, let's say, this dummy index here repeated twice, so it will give you the magnitude of, let's say, the vector a here. And I try to put this hat, this caret here, and not to forget it. So to further develop this concept, we can write something like, we'll see this in the transformation of the coordinate system. So if you have I prime, so this is the coordinate in the transformed coordinate. So you have this direction here, and you will have a tensor which you use this as, let's say, as a transformation, and using this you will transform this em here to this e prime I here. So here, of course, you will have to have something like qmi is equal to qmi em. So you will see here that again we have a free index, we have a dummy index. So m is a dummy index, and here we have I as the free index. And this is of course clear now for you that you have this m here, and this, let's say, m should be written as, for example, this, let's say, if you want to know what is the transform coordinate, so you will simply write something like, let's say, e prime 1 by putting I equal to 1, and here you will have, for example, m, because it is a dummy index, so m varies from 1 to 3, so q becomes 1 1 e 1 plus q 2 1 e 2, and you see here this is nicely changed, q 3 1 e 3. So let's say that if you have, uh, let's say, a tensor QMI here, so let's call it a tensor simply right now. So if you want to transfer it from 1 to 3 coordinate, so you want to transform it from 1 to 3 coordinate to the prime coordinate here. So you will have to do something like this. So E prime 2 is simply Q, M is 1, so I now is 2. So E1 plus Q 2, 2, E2 plus QM is 3, 2, E3 here. And you can see that 1 prime, 2 prime, 3 prime coordinate. So you want to do a transformation. Transformation from this to this coordinate. And E prime 3 is Q, so M is 1, because it resets for every expression here. So I is 3, of course. And this is E1 plus Q2, 3, E2 plus Q3, 3, E3 here. And you can also check this. So you have dummy index. So the number of terms in each expression should be 3 to 1. So you have one dummy index. So 1, 2, 3. And you have 3 to 1 for the free index, 3 to free index, which is 3, of course. You have I only as the free index. So you will, of course, have, let's say, 3 expressions here. 1, 2, 3. I for 1, 2, and 3. And this will significantly reduces the number of expressions you deal with in continuum mechanics. And later in stress analysis, stress strain analysis, and later, calculations. So next, we're going to deal with the Kronecker. I guess that I made a typo here. So Kronecker Delta. So this Kronecker Delta is a function which is quite used in mechanics and I guess in signal processing. I'm not sure about this, but I know that we use this in vibration analysis and also for impact analysis, where you have a huge force. So you say that okay, this function has a very is always let's say 0, but at 0 it is, let's say, infinity. So it has a very, very high value. So its usage is quite significant in impact mechanics and, let's say, vibration analysis. So we define Kronecker delta as delta ij. And we define it like this. So it is equal to 1 when, or let's say if, I is equal to j, if I is equal to j, and it is 0 if I is not equal to j. So for example, if you have an expression like let's say delta 1 1, so I is equal to j, of course. Here you have, this is I and this is j. So let's say that since I is equal to j, so you finally get 1. And this is also the same here for delta 2 2 is equal to delta 3 3 here. But for example, for something like delta 1 3, uh, this is I and this is j here. So I is not equal to j. Therefore, this value is equal to 0. This is also the same for 1, 2, delta 2, 3, delta 3, 2, and so on and so forth. And if we write this in the tensorial form, this delta ij, for, let's say, if we write a loop, let's say, in tensorial form, let's write it the Kronecker Delta in matrix form. It's better to say not tensorial form, in matrix form. If we write it, so if we gather this delta ij in matrix form, you will have 1 on the diagonal and 0 for the rest of the matrix. And this is actually equal to the identity matrix. And you have to take care of a very, very important point here. So I write here delta ij is equal to a matrix. However, previously I wrote something like delta ij is equal to a value. So this is completely incorrect. So I write this as this. So you never forget that delta ij, or the Kronecker delta, only refers to a value, whether it is 0 or 1. If you put it in a matrix form, it becomes an identity matrix where we show it by capital letter I, bolded, but I use, let's say, I here because I can't just rewrite everything as bold. So it becomes equal to the, let's say, to the identity matrix. So delta ij refers to a value. However, if we put it into a matrix, it will give us the identity matrix. We'll discuss about this later. So let's now write some expressions here and see what we get. So if we write delta ii, which is equal to, of course, delta jj, because we said that, okay, these jj and ii, they are the placeholders. They're just dummy indices. They are not important. We sum over them. So we say that, okay, delta 1, 1 plus delta 2, 2 plus delta 3, 3, which is equal to 1 plus 1 plus 1 is 3. So if I write something like delta 1m am, what I have here is that m is just a dummy index, right? So it varies from 1 to 3, for example. So delta 1, 1, a1 plus delta 1, 2, a2 plus delta 1, 3, a3. And nothing more than that. So, if, for example, this is a part of expression like delta I m a m, where actually I took the value of 1. So you can write the rest of the terms here for I equal to 2, I equal to 3. So we will have 3 terms and 3 expressions. 3 expressions, and of course 3 terms for each expression. So if let's write this for the rest. So you will have delta. So when I is equal to 2 and when I is equal to 3. So this is 2m am. This is delta to 1a1. 2 2a2 delta 2 3a3. I just write this for the sake of completeness because I want to show you something. So 3m am, this is 3 1 a1, 3 2 a2 plus delta 3 3 a3. And as you see here, you see a pattern. What does this equal to? So this delta I am that I wrote here, what does it equal to? So it is equal to an expression like a, because these are the let's say the dummy indices, so they are repeated. We don't put them on the other side of the equation. So we have only a free index here, I is the free index. So we have to repeat it, I. And you can simply put delta here. I mean, you can put delta I, but this doesn't give any meaning. So you have to put a I here. So it will give you a vector. So if you have something like let's say Kronecker Delta times a vector, for example, so it will finally gives you a vector. Let's check this. So this is 0, this is 1, this is 0, this is 0. So we will finally give you a 1. This is 0, this is 1, and this is 0. So it finally gives you a 2. This is 0, this is 0, this is 1. So it will finally gives you a 3. And what is this? So it is a1, a2, a3, or ai, where I varies from 1 to 3. Nice. Okay, we're going to the last topic in this video, which is the permutation symbol. And here, before getting into this, I would like to explain something for you, because I wanted to not discuss this because it might confuses you, but I guess this is quite important because you may face this in some extra, let's say, some advanced courses in mechanics, like fracture, where you work, for example, or in linear elasticity, where you have a plane stress or plane strain situation. You work with two, actually two in 2D. So most of the time, when we say, for example, if this expression, if we write it here, so this is let's say alpha m a m is equal to a alpha, and alpha here, where alpha is only 1 and 2, so it does not occupy 3. Or we can also show this with let me just delta beta n, for example, a n is equal to a beta, where again beta gets 1 and 2. So in two-dimensional problems, we have this kind of convention here. So we actually use alpha and beta instead of let's say I and j. So I thought that maybe this is something that you may come across, and it is quite important because you may get confused, but I thought that maybe you have to know this. So usually we use alpha and beta as 1 and 2, and I, J, K, R, S, and other kind of, Latin terms for let's say for 1, 2, and 3. But these Greek terms, alpha and beta, and sometimes gamma for 1 and 2. So let's get to the permutation symbol, the last topic in this video. So we defined this permutation symbol as epsilon I j k, and do not panic. So we define this as let's say 1 minus 1 and 0. So if if the number of permutation is even, and I will define the permutation in a minute. If the number of permutation of 1, 2, and 3 is even, so minus 1 if the number of permutation, or if the number of if the number of permutation is even, so if the number of permutation is odd, it is minus 1, and this is the case where we have otherwise. So otherwise it is 0. And what I mean by permutation, okay, by permutation. So the default value is 1 to 1. Let's write it this way. Okay, so you have 1, 2, and 3. This is the default value. So it is and it is equal to 1. So if you want to create, for example, like we want to know what happens to 2, 3, 1. Okay, so to manipulate this and convert it to something like this, we have to do something like, let's say, okay, so for the first one, so you need to swap 2 and 1. So you have 2 and 1, and you have 3 here, or let's write 3 like this. And in the second, so this is the first manipulation, or first permutation. And in the second permutation, you have this 2 and 1 here. So you have you have this 2 here. So it will remain as it is. And you swap 2 and 1. 3 and 1. So this is 3 and this is 1. So it's better to say that, okay, we swapped this with this, and here we swapped this and this. Okay, so this is the second permutation. So therefore you have an even number of permutation. Happens to 3, 1. Permutation, which is 2. But let's say, for example, this is the default value 1, 2, 3, and you want to change it to 3, 1. You want to convert it to 3, 2, 1. Okay, so you only need to swap. So the first permutation So you swap this with this. So you have 3 here, 1 here, and you have 2 here. So with only one permutation, we did this. Therefore, epsilon ijk is equal, or epsilon, let's say 3 to 1 here, 3 to 1 is equal to -1, and here, therefore, even number of permutation, therefore we had this epsilon 231 here. So we did it with 2 permutations, it is 1. So to get you a better pattern here, so we have 1 2 3 as the default pattern here. So these are even, so even permutations. So the default is 1 2 3 2 3 1. So you just push this here, 3 1 2, and then we reach as 1 2 3. So this is the same as here. So these are even permutations. So we can say that okay, epsilon 1 2 3 is equal to epsilon 2 3 1 is equal to epsilon 3 1 2 is equal to 1, for example. And the rest, you would say, are either -1 or 0. But when 0 happens, you see here, so if you have when 0, when epsilon ijk is equal to 0. So whenever you have at least 2 subscripts equal. So for example, epsilon 1 1 2 is equal to epsilon 2 1 1 is equal to epsilon 3 2 2 is equal to epsilon 2 1 2 is equal to the rest is equal to 0 here. We can also make another important conclusion here, that epsilon 1 2 3, as we noted here, is equal to, for example, 3 to 1 minus epsilon 3 to 1, for example. So we already showed this here. So we have epsilon 1 2 3 is equal to -1. 1 2 3 is equal to 1. Epsilon 3 to 1 is equal to -1. So these are equal to each other by a minus sign. But we can also extend this. Let me just remove this. So suppose you have a circle like I, J, and K. And this is the arrow here, these arrows here. They show the clockwise rotation. So if you have, for example, something like 1 2 3, it is 1. If you have epsilon 3 1 2, as we saw here, it is 1 again. If you have something like epsilon 3 2 3 1, it is 1. But if you move the other way around, let's say you have I, J, and K, and instead of moving in this direction, you move in this direction, you will have negative values. So these are positive values. So you will have negative values here. So let's say you have 1, 2, and this is 3. So these are completely these are in a clockwise direction. So if you say, for example, 3, 2, 1, 3, 2, 1, it is minus 1. 3, 2, 1. 1, 3, 2 is minus 1. 2, 1, 3 is minus 1. This is also recognizable from this here. So if you have, for example, 2, 1, 3, so we are moving in the opposite direction. So we have epsilon 2, 1, 3, which is minus 1. We have 3, 2, 1. So this is also minus 1. We also have some other rules which I would like to mention here. So we have the cross product and we have the dot product. So you know the dot product maybe. Maybe from high school or from bachelor's. So the dot product says that if you have a vector, we defined a vector here. We said that okay, so it is a okay, this is a vector here, so it can be written in the form of vector. So if you have two vectors here and you want to find dot product, let's say you have a dot b, and these are of course two vectors, the cross product. So the cross product, so it is the dot product. So the cross product, we show this with dot here, and here we show it with a cross. So let's say A cross B, we say that A EI cross B EJ. And so we have this A and B as the magnitude, so we can take it out, and then we have EI cross EJ. So if you have two different, vectors here, which are unity vectors, and we would like to calculate their cross product, so we can use the permutation symbol here. So we write this as, so we say that, okay, we have I and J, and here, as we wrote here, you have I and J. So finally, they will give a product of K. So for example, let me write it like this. So if you have E1 cross E2, so finally you will get something like E3, which actually comes from the fact that epsilon, so you have E1, 2, 3, E3. So it actually comes from this fact that this is also 1, so it is E3. So if we extrapolate this here, if we have EI plus EJ, so this becomes actually EK. So epsilon I J, I write them here, and then we have a third symbol, which is also a vector, because we expect that the result from the cross product of two vectors is a vector. So this is also EK. And as I already mentioned, you have I, J, and K. So if you have, for example, EJ cross EI, with the assumptions we made here, I, J, and K, so this becomes EJI, epsilon, JIK, JIK, EK. And we know that this is a negative value. Why? Because we have J, I, and K. So we are moving in the opposite direction. And the anti-clockwise direction of the default direction, which is the clockwise direction, which gives positive values here.